Greetings and welcome to a short class on chemical energetics from Learning Masters. We are dealing with chemical energetics as it is approached or taught in chemistry IGCE syllabus. Okay, so what we'll be studying in chemical energetics is energy changes in chemical reactions. So when we're studying chemical energetics, we're looking at the energy changes that happen in the chemical reaction. And we're not looking at all types of energy changes because we can study and investigate all sorts of energies that are possible during a chemical reaction. However, when we're talking about chemical energetics, we're talking about the energy changes that have to do with heat. In other words, the heat changes that happen during a chemical reaction. And just to recap, we measure energy in kilojoules, and we, we when we're looking here, we're quantifying or we're measuring an energy change. And usually we look at the amount of energy in the products versus the amount of energy in the reactants. So So what's written here is that 100 kilojoules of energy is given out when the amounts of reactants in the equation react together. The minus shows that energy is given out. So it's very important for you to understand that um, negative energy means heat being released from the reaction system into the surroundings. And we've already said that chemical reactions lead to energy changes, and we're specifically looking to heat changes. We're not looking at the energy it takes to move things around in the labs and such things. That would be considered mechanical energy. We're only looking at the heat changes in when reactions happen. And we classify reactions into two classes or two groups. The first group is exothermic reactions, and exothermic reactions release heat and they have a temperature rise. So, an example of exothermic reaction is a combustion of fuel. So, when we're dealing with an exothermic reaction, there's a couple of things we will see or we look at. So, first of all, if you're dealing with an exothermic reaction in the lab or in real life, so to speak, we'll feel heat because there's heat being released to the surroundings. In other words, we'll see a temperature rise if we're measuring temperature. So if you're doing a reaction in a beaker like this, um, when you have an exothermic reaction, you either see heat or smoke, or you'll actually feel the heat by touching the beaker. And of course, you can measure the temperature and see it rise. A good example of an exothermic reaction is a combustion of fuels. And combustion reactions are reactions that involve burning fuels in oxygen, or reactions that of metals with oxygen, or hydrocarbons with oxygen. So when you're dealing with combustion reaction, we're reacting hydrocarbon in oxygen, and we are releasing energy. So the heat changes are such that moves from from the system into the surroundings. Energy changes in a reaction. Like once again, the second class of reactions that we classify when we look at chemical energetics is endothermic. And endothermic reactions absorb heat energy from the surroundings. So it's from the surroundings into the system. And the word endo sounds like in, exo sounds like out. Just as endoskeleton is an inside skeleton, exoskeleton is outside skeleton. So endothermic means we're taking in heat, exothermic, we're pushing out heat. And endothermic reactions examples include cooking. For example, when you're cooking, what happens? You're providing heat from the stove, you're putting in the heat from the stove, you're supplying the heat, so that allows the reactions to happen. Another example is photosynthesis, where we have energy being taken in, and with photosynthesis, we absorbing radiant energy from the sun, and we allow that to cause the photosynthetic reactions to happen. So here's another short demonstration. The energy change is positive when we're taking energy in. The energy change is positive. The plus sign shows that energy is taken in. An exothermic reaction And endothermic reactions, we can represent them in what we call energy profile diagrams. And this is an example of an energy profile diagram. So what does the energy profile diagram show? It shows the amount of energy measured from in the reactants and the amount of energy measured in the product. And when you have an exothermic reaction, you one thing you will realize is that the energy of the reactants is higher than the energy of the product because energy is given out. So when you're looking at an energy profile diagram and you're asked if it's exothermic or endothermic, you will know that it's exothermic when the energy of the reactants is higher than the energy of the product. Similarly, similarly, when you're looking at an endothermic, this should say endothermic. Once I apologize, it's a typo. This should say endothermic. When you're looking at an endothermic energy profile diagram, you should realize that the product's energy is higher than the reactant's energy because energy is taken in from the surroundings. So when you're looking at an energy profile diagram and you realize that the product's energy is higher than the reactant's energy, then you should immediately know you're dealing with an endothermic reaction. Okay. Now, how can we compare these energy changes to bonding? So energy. So when we're looking at bonds, two things happen. Existing bonds are broken and then new bonds are formed. So in order for bonds that already exist to be broken, energy needs to be absorbed. Imagine it like this. We've kept two things tied together like this. Now we need the balls to break apart so we can rearrange them with other balls. Then we need to input energy to break these balls apart that we have tied together. So when you want to break bonds, which is one of the things that happens when reactions happen, energy is absorbed for bonds to be broken. And when new bonds are formed, then energy is released. And exothermic reactions occur when the energy absorbed to break bonds is less than the energy released when new bonds are formed. And endothermic reactions occur when the energy absorbed to break bonds is greater than the energy released when new bonds form. So you have an exothermic reaction happening when the energy that is released when bonds are broken is higher than the energy absorbed when bonds are formed. And when you're dealing with an endothermic reaction, you will find that the energy that is absorbed to break bonds must be greater than the energy that is released when new bonds formed. And we have a term in science called the bond energy, which we can define as the amount of energy absorbed to break existing bonds or the amount of energy released when new bonds form. So we can calculate bond energy. So when you're dealing with H2, HH, and Cl2 to form hydrochloric acid, HCl. So hydrogen is H2 and chlorine is Cl2, and HCl is hydrochloric acid. So when we form that, and then we balance the equation, so that's where the two comes from. And then when we can draw it out like this, then we find a table. We have an energy table that tells us the amount of energy in an HH bond, the amount of energy in the Cl bond, the amount of energy in the HCl bond. So when these bonds, these are in the reactants, and these molecules need to be broken apart. So an energy needs to be taken in. When we want to calculate the total energy changes in the reaction, we look at the reactant bonds that because these are the bonds that were already existing, that these are the bonds that need to be broken, and the energy associated with these reactants is going to be positive because energy needs to be taken in to break bonds. These bonds need to be broken, and so energy needs to be taken in. When energy is taken in, that is associated with a positive sign in energy calculation. So we have one HH bond, and we found this 436 kilojoules from an energy table. It's positive because it's energy taken in. So in the same way with the Cl, we find the value from the energy table is plus because it's energy taken in to break the Cl bond. So the total energy we've taken in is 678 kilojoules. And now we look at the products. Remember, when we form products, when bonds are formed, energy is released. So the energy that is associated with the product is going to be negative because energy is released. And we have from our balancing chemical equations, we know where the two comes from. And so we have two HCl bonds. So then we find the value from an energy table of one HCl bond, which is 431. Then we multiply it by 2 because of that stoichiometric coefficient. However, it's going to be a negative assigned charge because it's bonds, because energy is released when bonds are formed. Then we find the total energy changes in the reaction by taking the total energy in minus the energy out. The total energy in is positive, plus the energy out, which is going to be a negative sign, and then we get minus 884 kilojoules. And since it's negative energy, we know that this means the reaction is exothermic and energy is being released. So, and then we can show this also in an energy profile diagram. Remember, when we looked at energy profile diagram for exothermic reactions, the energy of the reactants is higher than the energy of the product. So there's the energy of the reactants, here's the energy of the products. Clearly, it's higher as it should be. As I said earlier on, it's an immediate giveaway. When you see the energy of the reactants higher than the energy of the products, then you know you are dealing with an exothermic reaction. Here's another example, ammonia breaking down, NH3 breaks down into N2 and H2. We repeat the process, but now this is our reactant. So here the bonds are being broken. So we have one, two, three NH bonds, but times two. So we actually have six of them. And this is the value we find from the energy table. It's plus because it's energy taken in. And these bonds are formed, all of these bonds are formed, so energy is going to be released here in the product. So we find the nitrogen triple bond energy value from a table, and we're going to add it from the hydrogen double bond, and we multiply it by the 3, and then we get the total energy out. But remember, energy out is always negative. So then we combine the total energy in minus the total energy out. Then we find the value to be 92 kilojoules. And 92 kilojoules is positive, so this reaction is overall endothermic, and we expect that the energy of the product is higher than the energy of the reactants because energy is taken in. And here's your energy profile diagram. And that puts us at the end of this lesson. I hope that was helpful. I really hope that was helpful. In another lesson, we'll hopefully look at how these questions look in past exams. Otherwise, we'd be more than happy to take a lesson with you at Learning Masters. Check out our website, subscribe to our YouTube page, like our Facebook page, and follow us. Thank you.